All right, so what we're doing today. So we have talked about how to take parent functions and mess around with them. Guys, you ready? Okay, so what have we done so far? Well, what was the first thing we learned about? Up, down, left, right? So maybe something like this, f of x equals, I don't know, x plus 2 squared minus 3. That would move it left 3, down 3, right? Left 2 down 3, thank you. And then what else did we learn about? So that was one of them, right? What else?
Absolute value.
Well, what the parent function is less important than what was happening. What else other than moving left, right, up and down? They can also reflect or flip, right? And that might look like this, f of x equals negative square root of x, right? So today we're going to talk about, well, what's one thing we've added and subtracted from them a couple different ways. We've negated them. What have we not done to them? Well, there's adding, subtracting, and multiplying and dividing, right? So we can multiply them as well, and then that does something totally different. So we don't really talk about it as dividing, we talk about it as like multiplying by a fraction. It's just easier to think of it that way. But yeah, multiplying and dividing, so you might have something like this. F of x equals 3x squared, right? And we gotta think about what would happen then. What would that do? And just like all our other ways, we're gonna do it the long way with the old XY table, and then we're gonna talk about the short way if you know the pattern, okay? So that's our plan. But before we get there, our warm-up was multiplying some fractions. And the reason that we're multiplying fractions is that we're gonna have to do that in our moving around of our function, okay? So there's always a point to the warm-up. It's a skill that I want you to use during the lesson. So let's talk about it. Now, there's a couple different ways to do these problems, right? There's the, oh, I kind of just know the answer. And then there's the, hey, I know the answer, but I'm going to go through the process because there's going to be times where I don't just see it, okay? So for instance, if you got 1/2 times 8, you might have looked at this and said, well, I know 1/2 of 8. What is 1/2 of 8?
4.
4, right? So I know this is 4. But this is a pretty simple problem. What if I said, tell me 3/4 of 40, right? And you're like, well, I don't really know that off the top of my head. I wish I had a process. So we process with simpler problems so that we have them for harder problems, right? So the process would be, okay, how do I multiply a fraction by a number? 1/2 times 8. Anybody know?
Put a 1 below it.
Say again?
Put a 1 underneath 8.
Yeah, put a 1 underneath 8. Because now I have 2 fractions, and we know when we have 2 fractions, we just multiply across, and we get an answer. So multiply across, I get 8 over 2. 8 divided by 2 is 4. That confirms what we knew to be true, which is that 1/2 of 8 is 4. Question?
So I don't do the put a 1 under, I just multiply
The top?
by the numerator.
What if the numerator wasn't, okay, so you just say to yourself, 8 times 1 is 8, divided by 2 is 4.
Yeah.
Yeah, I mean, you're essentially doing the same thing in your head, right? Now, the reason that you don't need to do all this is because you're recognizing in your head that 2 times 1 is just 2.
Yeah.
Yeah, that's fine. You don't have, this is just the long process if you need it, right? Some people can just do that, some people can't, right? So we want to make sure we have a process. All right, same thing here. I got 1/3 times 9. So that'd be 1/3 times 9 over 1, right? Multiply across, 1 times 9, that's 9. 3 times 1, that's 3. 9 divided by 3, that's 3. And you might have thought to yourself, yeah, I knew that 1/3 of 9 was 3. But now you've confirmed it, okay? And here's where the process starts to be helpful, because you might look at 1/4 times 2 and say, that's 0.5. But maybe you don't. This is where it starts to get a little more complicated in your head. So then you use your process that you've practiced on easier problems. You say, okay, 1/4 times 2 over 1, multiply across, I get 2 over 4. Now let me tell you a mistake that I see a lot. Students get 2 over 4, and they tell me, oh, 4 divided by 2, that's 2. They just start doing the division. And they don't recognize, well, actually 4 is on the bottom. It's 2 divided by 4, not 4 divided by 2, right? And that is an example of getting lost in the sauce in the process and not using your noggin to sense check it. Think about it. If I got a small number divided by a bigger number, how could I get a whole number, right? It's got to be a fraction. It's got to be a decimal, right? Hey. Thank you. So 2 divided by 4. You might say, oh, I know that that's 1/2, but maybe you don't, okay? Maybe you have to just think about it and go, what goes into both of those? Well, 2 goes into both of those. So I'm going to divide both of these by 2 to reduce it. And 2 divided by 2 is 1, 4 divided by 2 is 2. So now I know this is 1/2. So 1/4 times 2 is 1/2. So, last one. All right, 1/3 times 4 is, okay, this is an example of why we don't want to just use our calculators all the time. Because if you did 1/3 times 4, anybody do it in their calculator? I didn't tell you not to. So maybe you did, and that would be okay. If you did, somebody tell me what you would get. 1.3333 forever, right? Forever. And we only have so much time in the day, so what you probably do is on your paper, you'd say, okay, that's about 1.3, right? That symbol means approximately.
I would do the 1.2 with the line on the top of the 3, because that signifies that it would be considered.
That would be good too, yeah. You could say it equals 1.3 repeating. But what if you got a number that was like just not even repeating, it just went forever, like pi, right? Something like that. Just went forever with different numbers. There's no way to round it and make it exact. What is exact is if you left it in a fraction. So in this case, if somebody asked you for the most precise answer, you would say, I'm going to leave as a fraction. You'd have 1/3 times 4 over 1, multiply across, you get 4/3, right? And you're tempted to do more with that, but 4 doesn't divide by 3. You can't reduce them. So it's totally acceptable to say 4/3, right? As the answer, because that's actually pretty accurate. Because now somebody else that they needed that to build a spaceship would get the exact measurement that they needed, not a rounded one. Does that make sense? Okay, so why did we practice fractions? Well, we're going to be dealing with some fractions today and multiplying by them, okay? So, notice which ones were a lot simpler. The ones where the thing on the bottom and the thing on the side had a relationship. You could divide 8 by 2. You could divide 9 by 3, right? This one, not so much. This one, not so much. So we want to look for those friendlier relationships when we're graphing with fractions. And I'll show you what I mean when we get to that example. Okay, so we have this parent function, right? Which parent function is this? It's absolute value. The parent function is the absolute value of x. That's what we're starting with. And we're going to see what happens to it when we put numbers in the front of it, when we multiply it, okay? This parent function, we know, goes over, well, first of all, it starts at 0, 0. And it goes over 1, up 1. It goes over 2, up 2. And so on and so forth. It goes over 5, up 5, right? So that's the movement of the parent function. Eventually we're going to look at what happens to those movements when we add a multiplier in the front, okay? So before we do that, let's just graph one the old-fashioned way. So let's talk about this right here. We have 2 times the absolute value of x, okay? Now, remember when you were working the warm-up, I was like, hey, it doesn't always have to be -2 to 2. We love to just go -2, -1, 0, 1, 2. Gives us all those points. If I do that in this one, it's like right here. Like this is a huge graph. Let's use it. Let's spread out, right? We still want to have 0 in there.
Why do we have to have 0?
Because you want to know what happens in the middle. You kind of just always want to know that, right? What happens at 0. But hey, let's branch out a little bit, right? Let's go to -10, let's go to -5. So I'm going to go, let me change the color on this here. I'm going to go -10, -5, 0, 5, 10. So we can spread out our points a little bit, not bunch them all up. Does that make sense? Okay, so what do we do? Well, we plug each of these into our function. So this would equal this y value, right? That's what we're looking for here, would be 2 times absolute value of -10. What's the absolute value of -10? 10. So this is 2 times 10, which is 20. So 20 is my y value at that point. This would be 2 times the absolute value of -5. That's 2 times 5, which is 10. What is 2 times the absolute value of 0? 0, right? Absolute value of 0, 2 times 0 is 0. So this is just 0. And then, anybody want to guess what it would be for 5? How do you know?
Same thing.
Yeah, because this absolute value of -5 is the same as the absolute value of 5, right? So this thing would turn into the same thing, and it would be 10 again. And that's why this thing is symmetrical, right? On both the negative and positive sides. So if you needed to, you could keep calculating each of these, but we're just going to fill these in, okay? So that's -10, 20, -5, 10, 0, 0, 5, 10, 10, 20. Let's look at the graph, right? So this graph that we're about to do is 2 absolute value of x, right? 2 times absolute value of x. So we got -10, 20, -5, 10, 0, 0, 5, 10, and 10, 20. Okay? We add our lines. And this is what we end up with, okay? So, what happened? What happened when we multiplied? Just in your own words, what do you think? Compare the blue one to the parent function. What happened when we multiplied? Thinner. I heard tighter. Any other words? Yeah. Steeper. Yep, all accurate. Now, the word that we use to describe this, stretch. So what I want you to think about is if this black function was a rubber band and it was just kind of hanging out like this, and then you took the top of the rubber band and you multiplied the force that you pulled it with, what would happen? It would get thinner and stretch. The rubber band would stretch. So the rubber band would be like this, and then it would go like this, right? You're stretching the rubber band because you're multiplying the force that you're pulling on it with. Okay, so that's what we call this. We call it a stretch. And when we talk about a stretch, or the next thing, right? That's really messy. When we talk about a stretch, we talk about it in terms of its factor. How much did it stretch by? Oh, well, this stretched by a factor of, anybody know? 2, right? That's what you multiplied by, right? So that's your factor. Factor is what things that multiply, right? Excuse me. So this is your factor right here, this 2. right? So we stretch by a factor of 2. So if somebody said, hey, what transformation happened to this function? You say, oh, it was stretched by a factor of 2, okay? Just like before you would say, oh, it was translated right 5. Oh, it was reflected over the y-axis. Well, now we would say it was stretched by a factor of 2, okay? So that's a stretch, okay? So, let's take a look at what happened to our pattern. So this is our original pattern, right? Now let's talk about the blue pattern that we see. Okay, so for f of x equals 2 absolute value of x, our pattern, we start at 0, 0, and then where did we go? We went over 5 up, not 20, 10. So we went over 5 up 10. We went over 10 up 20. Those are just the points that we found. What if I went over 4? How much did I go up? 8. What are we noticing?
You're half of the,
X is half of the y. Compare this to what the black function was doing. Remember? This one went over 5, up 5. It went over 10, up 10. It went over 15, up 15. It went over 20, up 20. Right? It went over 2, up 2. But this one went over, instead of over 5 up 5, it went over 5 up 10. It went over 4 up 8. Instead of over 10 up 10, it went over 10 up 20. Every one of the upward movements did what? Doubled, because we are multiplying by 2, right? So the takeaway here is the up and down, if you're going down movements, get multiplied by your factor. So instead of going over 5 up 5, we went over 5 up 5 times 2, which is 10. Instead of over 10 up 10, we went over 10 up 10 times 2, which is 20. Okay, so you're multiplying the movements up and down by your factor. Make sense? Okay, let's graph this other one, this other situation that might pop up. So here's another reason why I was like, okay, I know that you got -2 to 2 down, right? But anybody do -2 to 2 and get some really weird, hard to graph points? I know you did because I walked around, I saw, right? So what would have been a kinder thing to do to yourself? Because you get to choose whatever x you want, right? And you know you're going to multiply by 1/5. What numbers are really good to multiply by 1/5?
10.
Multiples of 5, right? So 5, 10, 15, 20. Those would be easy multiplication by 1/5. So let's go easy on ourselves here. And let's choose some of those numbers. So let's mix it up. Let's go -20, -10, 0, we always like to include, and then we'll go 10 and 20, right? If you chose 2, you're gonna end up with like 2/5, and like, how do you graph that, right? It's hard, but these will give us nice clean points, and you'll see why. All right, so for the first one, it's 1/5 times the absolute value of -20. Well, what is the absolute value of -20? 20, so this becomes 1/5 times 20, and now it's like our warm-up problems. Put it over 1, right? 1 times 20, 5 times 1 gives me 20 over 5, which is 4. So at -20, we're gonna be at 4. See, I got a nice clean point out of that because it was divisible by 5. Okay, so be kind to yourself. Don't make it too hard on yourself. All right, keep going, I'll remember. All right, so 1/5 times absolute value of negative 10. That's 1/5 times 10. You can turn that into a fraction, or you can just think, I know 10 divided by 5 is 2. All right, we know the absolute value of 1/5 times 0. Well, I'm sorry, the 1/5 times the absolute value of 0 would just be 0. And we know that this thing is symmetrical, so what do you think 10 is going to be? 2. What do you think 20 is going to be? 4. All right, so let's see what happens. So at negative 20, I'm at 4. That's it. I only went up 4. At negative 10, I went up 2. At 0, I'm at 0. At 10, I'm at 2. And at 20, I'm at 4. So I grab my ruler. I end up with this. Okay. And let's talk about what happened. Here we multiplied by 2 and it stretched everything. Here we multiplied by 1/5, a fraction, and what did it do? How would you describe what happened with the right function?
Seems less intention.
Yeah. So instead of,
Opposite of stretch.
all right, here's another good example. Instead of a rubber band, think of a balloon. The balloon starts like this, you blow it up and it stretches out. The balloon stretches out. And then you deflate it. What happens to the balloon?
It gets smaller.
What's the word for that, getting smaller?
Shrivel.
Shrivel? Close. Shrink. Very good. Yes, it would shrink. So that's the word we use. This is a shrink. Yep, it's a shrink. And we also say by the factor. So by a factor of 1/5. Okay? So we got a stretch and we got a shrink. And think about those movements again. Remember we said, well, typically you go over 5 up 5 for the parent function, or you go over 10 up 10. Well, we went over 10 up 2. Instead of going up 10, we went up 2. Because we took our movement of 10 and we multiplied it by 1/5, and instead we got 2 and moved up 2. Okay? Question?
In shrink problems, would the slope from 0 to 0 and either, or for this problem specifically, just
For absolute value.
yeah.
But not like what if you're doing with a parabola or something. Yeah.
Why do we call it shrink? I'm confused.
So shrink, honestly, stretch and shrink aren't the best words. They are the words that have been accepted as the right way to say it. Whatever way you remember it, as long as you're showing me you understand what's happening. So for instance, let's say that's a good transition to these questions. What did putting an integer in the front, meaning a number in the front, not a fraction, what did that do to the function? Whatever words you want to say. When we put the integer in the front. You said a lot of great words when I first asked, what's happening here?
Stretch.
Well, stretch is the official word, right? But how are we going to help ourselves remember it? What else happened? It went from this to this. It got what? Tighter is good. What else? Yeah, skinnier. I feel like somebody else said something that was pretty good. Steeper. Somebody said steeper, right? Right? This is how we're going to help ourselves remember this stuff. If on a test you told me it got skinnier and you didn't say it stretched, I would consider that, right? I'd be like, well, they kind of understand what's going
You
on.
got more in
All right, so what about when we multiply by a fraction?
Shrinker?
It's shriveled. I love that. I've never heard that one. It's shriveled. We say it shrunk, right? Well, it was like this, and then it got to this.
Fatter.
Fatter?
Fatter. You got fatter.
That's not very nice. This function has feelings.
It got wider.
Bigger.
Yeah, well, bigger could be anything. Wider. Let's say wider. It got wider.
It got taller in the horizontal direction.
Yeah, there we go. There we go. Now we're being polite. So it got wider. A lot of people say it looks like you took the function and you
Crushed it.
crushed it or
Crushed it,
squished it, right? It gets like squished.
What about chocolate?
All right, back to the lesson. All right, so let's go to the next side. Let's sum up what we've talked about here. All right, so when you have a number out front, right? You got this number out front. It can be one of two things. It can be greater than 1 or less than 1. That number is what we call the factor, right? And you want to be able to use that word. Hey, it's a factor of 2. It's a factor of 5, whatever, right? Now it says there's two possibilities, greater than 1 or less than 1. Why isn't 1 an option? What do you think?
Because that's
Anything
that's
multiplied
the
by
regular.
Yeah, that's the parent function, right? 1 times absolute value, nothing would change. It wouldn't get bigger or smaller. So it's either greater than 1 gets bigger, smaller than 1 would get crushed, or whatever way you want to remember it, right? So again, one more time, let's use these words. A number greater than 1 stretches it.
Yes.
And I'll draw a little picture for you since we don't want to just think about absolute value. Like, let's think about the quadratic function, right? We got this quadratic function here. And then if I stretched it, well, it would start in the same place, but like a rubber band, if you pulled on it, it would go like that, right? It would get skinnier, it would start stretching out. And then a fraction would shrink it. And if we're thinking about that same parabola parent function, well, this one would kind of get squished, right? It would start at the same place, but all its values, all its outputs would get decreased by a multiplication factor, and they would shrink, and it would look like somebody's squishing down on the function.
It's a smiley face.
Is it?
You don't see it?
I don't see it. Is that the nose?
No,
Yeah, it's a
that's
smiley
the,
face.
that's the eyes, is the
Dot
top
is-
part of the collab.
The da is the nose?
And-
Yeah, it's a smiley face.
Oh yeah, it is. Nice. Sometimes my lessons are better than I even know. I'm putting hidden smiley faces. All right, so let's keep going. All right, let's do a few examples and then I'll give you your homework. All right, so let's say you had a graph 1/3 absolute value of x. Okay. Well, we know that typically the absolute value function looks like this. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. And then the same thing on the other side, right? This is our parent function. That's what it typically looks like. And now, what's that?
For the homework, are we gonna have to draw this parent function or is it like?
Oh, you're saying, like, do you need to? No, I'm saying I'm doing this to help us right now. If you don't need it, you don't need it. I do want you to recognize the pattern and not just be knocking out X, Y tables every single time, because that's more work than you need to be doing, okay? So, in this one, remember we multiply our movements by our factors. So our parent function, y equals absolute value of x, goes over 1 up 1. It goes over 2 up 2. It goes over 3 up 3. What do we say to do with our factor? I said the movements change according to the factor. How?
It
We wrote it on the front if you want to look back.
lower.
No.
Well, it depends. If it's a fraction, it would be lower. Okay, but what do I do to find the value? Because I need to be able to go over and up something.
You have to multiply
Multiply.
the number with the over 1
1 over 3.
So I'm going to multiply this number by my factor, right? So I'm still going to go over 1, but instead of going up 1, I'm going to go up 1 times 1/3, and then 2 times 1/3, and 3 times 1/3, okay? Now, you're going to get some funny points, so you kind of want to start thinking about those kind numbers again. Which one of those is going to be a kinder one? 3 times 1/3 is what? 1. So this one would be a nice one. Over 3 up 1. So I'm starting at 0, 0, over 3, up 1. Back 3, up 1. Right? That's easy, right? What would be another easy one to go to?
6.
So normally we go over 6, up 6.
Over 6 of 2.
Yeah, over 6 up 2. Instead of 6, we do 6 times 1/3, which is 2. So I go over 6 up 2. And I go back 6 up 2. Okay? All you need is some decent points, right? It doesn't have to be right the same points every single time. Yeah, question?
So then it would be, over 9 up 3.
Exactly. Over 9, usually we go up 9, but we're multiplying it by 1/3, our movement up, so we go up 3. And I go back up 3. And it gives me this. And you would use a ruler because you're not crunched for time like your teacher.
Why is it over 3 up 1? Because you multiplied it?
We multiply this by our factor. This factor right here up front. Yep, good. All right, so that gives us our function, right? And you notice, we can sense check it. We multiply by a fraction, so we were expecting it to shrink. And if we compare our blue points to our black points, it shrunk, right? Okay, now you might need to write a function, right? So you might need to do this in reverse. You might say, well, I know my parent function is f of x equals absolute value of x. And I know that when we multiply, we put a number out front. So I need to figure out what that factor is. So it's going to be f of x equals some number times x, right? Now, I have to look at the pattern. Now, normally, our function goes like this, right? So we got to look at what happened instead. It didn't go over 1 up 1, it went over 1 up what? 4. It didn't go over 2 up 2, it went over 2 up 8. So what is it multiplying by every time? 4. So there's the factor of 4. So that goes right here, and that's my function, 4 absolute value of x. Okay? And you can always check Desmos to make sure you're doing it right. Right? Plug it into Desmos and be like, I think I got this, but let me make sure it's behaving the way I think it will. Yeah?
What if your Desmos doesn't work? Can you just use a scientific, not?
Well, I mean, when I say Desmos, it's because everybody's got access to Desmos. If you have a graphing calculator, start using it, getting used to it, right? So if you have a graphing calculator, sure, check it there. Yeah, yeah. It's just, Desmos is just an option. Okay, last one. So far, we've been given a function and we had to graph it. We were given a graph and we had to write the function. Now we're gonna do one more that's like the first one, but it's quadratic. So we're given the function and we're asked to graph it, okay? So we got 3x squared, right? Well, what's our parent function?
Over 1 up 1.
Well, what's the name of our parent function?
Quadratic.
It's quadratic, and we know our quadratic parent function is normally, before it had children, x squared, right? Remember, children, these are all children of the parent. Think about it, children look very similar to their parents. Do they ever look exactly like their parents? No. But they have a lot of the same characteristics and the same patterns, right? Some good, some bad. All right, so we graph our parent, if we need to, 0, 0, 1, 1, 2, 4, 3, 9, right? And our parent is going to be our guide to what we do, okay? Now, what's our factor?
3.
Our factor is 3, right? So instead of over 1 up 1, over 2 up 4, right? What are we going to do? I'm not going to go up 1, I'm going to go up 3. I'm not going to go up 4, I'm going to go up 4 times the factor, 12. Does that make sense? So watch what happens. I start at 0, 0 still. I go over 1 up 3. I go over 2 up 12. And then I know I can flip those points backwards, or I can do the same type of multiplication backwards, and I end up with this function, this parabola, stretched out. And I know I did it right because what kind of number was in front? A fraction or an integer? An integer, and integers make things stretch. Does that look stretched compared to the parent function, or squished? Stretched, so I know I can feel like I did it correctly. Okay? All right, so tonight you're going to practice that, right? Tomorrow we're going to do a little bit more complicated stretches and shrinks. That's it for the unit, though. Monday we review, Tuesday we test. Okay? Question?
Why over 2 up 12?
Because first, normally, think about the parent. The parent goes over 2 up 4, right? Our factor was 3. So we don't go up 4. We go 4 times 3, which is 12, and that's all the way up here. Great question. All right? All right, homework.